Hello, today we will talk about Coriolis Force. Coriolis Force is the last great important force that we need to describe before we can cast Navier-Stokes equations. This force is also fictitious or apparent force and a consequence of applying second Newton's law to non-inertial reference frames, or in other words, the surface of the Earth being non-inertial reference frame. In today's video, I will demonstrate to you the existence of Coriolis force using very simple experimental setup that you can do at home. Then we will mathematically derive the components of the Coriolis force. And third, I will show to you the existence of Coriolis force and action of Coriolis force in real measurements carried out in sea current in the Baltic Sea. Let's first demonstrate the existence of Coriolis force. To demonstrate the nature of Coriolis force, I will use this very simple setup. Here I have a piece of the cardboard, that I attached to the background that is not moving. So my background is basically inertial frame of reference, whereas this rotating cardboard is non-inertial frame of reference. Now, first what I will do is I will draw a line between the center, the pin, and this X when I am not rotating cardboard. So this is very simple. This is the line that connects the center or the pin and the X, which is the point that is not moving. Now I will draw the same line, but I will rotate this board here. And I will do it sequentially. Namely, I start by drawing the first dash in this dashed line. Now I rotate, and I always go towards the X. Now from here I go towards the X. Then I rotate more, I go towards the X. I rotate more, I go towards the X. I rotate more, I go towards the X. I rotate more, and you can see that in all cases I tried to go towards the X. My goal did not deviate, so to speak. From the point of view of each of these elements, I was going straight. But from the point of view of the rotating frame of reference, I curved. Let's try it again. So, I always want to go to X. So, I go straight, but I'm rotating, and look, I'm drawing straight line, but because I'm rotating the whole system, the line ends up being curved, Coriolis force. It works in any direction. Here I have a different line, so if I start from here and I want to go towards this point, let's say I make one jump, then I rotate. Now from this point I continue going straight towards here. I rotate. I try to go towards this dot. I rotate further, and you can see that again I will exhibit circular motion. So this is very simple experiment that you can do at home and convince yourself that in non-inertial reference frames result in these apparent accelerations or forces that are not there if we are in inertial frame of reference. Namely, if I'm not rotating this board and I want to draw straight line between this point and the X, the line is indeed straight. But when I started rotating, the curvature appeared, and the curvature is the consequence of non-inertial frame of reference. Now I highly encourage you to try to repeat this experiment at home and convince yourself that there is a profound, huge difference between inertial and non-inertial reference frames. Now let's go and mathematically derive this curvature that we see in this demonstration. We saw that Coriolis force, and I will call it FCO, is equal to minus 2m omega cross product V, where v is velocity measured in respect to the Earth's surface, and omega is angular velocity of the Earth. I can also rewrite this, knowing the properties of the cross product, as 2m v cross product omega. This is further equal determinant. So v cross omega, we know that the first row are the unit vectors I, j, k. The second row are the components of v vector, which is u, v, w, where u is from west to east, so positive eastward. V is the meridional component from south to north, so positive northward. And W is the vertical wind component, so positive upwards. Components of omega from my previous video on the centrifugal force, we know it's 0, omega cosine phi, and omega sine phi, where phi is latitude. And of course, I have to multiply all this with 2m. With 2m because I have 2m here. Now I need to solve this determinant, which is not that difficult. It is equal to m that multiplies. Multiplies what? Well, first I cross this column and this row, so I will get v omega sine phi minus product of this is w omega cosine phi times the e component minus, in the j direction, I see I will only have u omega sine phi times j, and in the k direction I will only have u omega cosine phi in the k direction, k unit vector here. Okay, I hope you can see all that. Now I will introduce a substitute f that is equal to omega sine phi, and another substitute called phi prime that is 2 omega cosine phi, because you can see that 2 and these omega sine phi and omega cosine phi are in all these terms, so it is useful to introduce these substitutes. And then Coriolis force has the following components: m, which is mass, and then component in the I direction is Vf minus Wf prime. Component in the j direction is clearly minus Uf, and component in the vertical or k direction is clearly Uf prime. And this is expression, or rather components, of the Coriolis force. Now, what we did for all previous forces, we will do for Coriolis force too, and that is we want to express this force in terms of the second Newton's law to see how we use it in the second Newton's law. In that case, we know that mass times acceleration is the sum of all forces. I will cancel this mass and this mass in all terms, so I don't have to write it further. Then the acceleration in the x direction, du dt, will be this, Vf minus Wf prime. Acceleration in the v, in the j direction, or the v component of acceleration will be minus uf, and acceleration in the vertical direction will be this third component, uf prime. We see that if the air is moving eastward, which means u is positive, dv dt will be negative because of this minus on the northern hemisphere. So the deflection will be towards the south. Let's put that here in the quantitative form, so to speak. If u is positive, we see that minus u is then negative, which means dv dt will be negative, which means towards the south. Opposite will happen in the southern hemisphere because f, which is 2 omega sine phi, is actually negative in the southern hemisphere because sine phi is negative. In the first equation, we see if v is positive, then du dt is also positive, which means we will have an eastward deflection. So if we have motion that is in the northward direction, the acceleration due to Coriolis force will be towards the east. Opposite again holds in the southern hemisphere. I hope you can also see from the first equation, for example, that if the motion is upward, which means W is positive, let's put it here also, W is positive, then du dt will be negative because of this minus, which results in the westward acceleration. On the other hand, if we have downward motion, then this term is positive, so du dt will be positive, and that is eastward acceleration. And because f prime is 2 omega cosine phi, and cosine phi doesn't change sign from north to south hemisphere, we see that this rule in the vertical direction is independent of the hemisphere, which means the same will be observed at the southern hemisphere. Now, since W is typically much smaller than either U or V components in the case of atmospheric motions, we usually neglect all terms associated with W, which means this term would be usually neglected. And since accelerations in the vertical directions are also small, we usually neglect this term too. So most common is to see the Coriolis term playing only the important role in respect to f. Wherever we have f prime, we usually neglect these terms. Not always, but usually. Coriolis force is always deflecting air parcels to the right on the northern hemisphere. And we can conclude that the motion due to Coriolis force would therefore be a circular motion. In other words, let's assume there is this air parcel that is given an impulse force to the right, and the force stops. That's called impulse force in physics. Namely, we basically give it some initial velocity towards the right, and then the force, let's say the pressure gradient force that initiated this motion, ceases to exist. So in an inertial frame of reference, this parcel of air would continue coasting forever if there is no roughness and other forces. In non-inertial frame of reference, due to Coriolis force or Coriolis accelerations, it would actually exhibit, so if this is our air parcel, it would start to exhibit circular motions because Coriolis force is constantly acting to the right. So in every point in time there is force acting inwards, but at the same time, since the parcel is coasting to the right, it would continue coasting to the right, but it would have this spiraling motion. And these oscillations are called inertial oscillations. We also see that the Coriolis force is the smallest at the equator. At least the F term is disappears at the equator and has the highest value at the poles. The opposite holds for the vertical component. The fact that Coriolis force is zero at the equator is one of the reasons that the weather systems in mid-latitudes are profoundly different from the tropical weather systems. That's not the only reason, but it's one of the important reasons. That's it. The only thing that is left is for me to convince you that this force really exists, and for that we need some real measurements from either oceans or the atmosphere, and these measurements are much simpler in oceans rather in sea, and here I will show to you the existence of inertial oscillations in real measurements in a sea current. Here we see the famous measurements carried out by Gustafsson and Kullenberg in 1936. The measurements of inertial oscillations in the sea current were carried out in the Baltic Sea. Baltic Sea is suitable for these types of measurements because it has very small tides, it is isolated from the Atlantic Ocean, and the tides are only a few centimeters, which prevents contamination of these types of measurements due to tidal motion. So this is not in the atmosphere, it is in the sea. These types of plots are called the progressive vector diagrams, and they show the track of an individual water element that we see here that originated here, and it was carried out with the sea current that is flowing in the north-northwest direction, but inertial oscillations are clearly superimposed on the current. We see the regular circles. The period of this circular motion is 14 hours, and if we calculate the theoretical period from the equations for Coriolis force, we get that at this latitude the period of these inertial oscillations should be 14 hours 14 minutes, and the observed value is 14 hours. These numbers represent days, so the measurements were carried out between 17 and 24 August 1936. If we show the decomposed velocity into the components, which is here, you can see components of the velocity in the north and east direction are very periodic. The amplitude is very similar, and this is also something that would be predicted theoretically. It is interesting to note that as the current is approaching land, the oscillations are damping out. And this is expected too, because friction starts to play a more important role and the Coriolis force therefore diminishes. So, at the end of this video, you learned how to demonstrate the existence of Coriolis force using simple cardboard experiment. You also know how to mathematically express this force if needed, and I convinced you using real measurements in the sea current that the Coriolis force really exists. In the next video we will see under which circumstance we can neglect this force, because by now you probably realize when you go down the road to grocery store to buy milk, for example, you don't start spinning around exhibiting inertial oscillations, which means Coriolis force is not so important. When you drive car, you don't start deviating from the road, which means Coriolis force is not so important. And in the next video, on the Rossby number, we will see when we have to account for Coriolis force and under which circumstances we can neglect it. This video is originally published on December 31st, 2020, which means it's New Year Eve. I want to wish you Happy New Year. But if you are watching this video in the future, let's say June 2nd, 2022, it's still New Year because Earth is going around the Sun in a circular orbit, which means we can start measuring New Year from any date whatsoever. What is more important though is the fact that I said Earth is going around the Sun in a circular orbit, which means that the center of the Earth is not actually inertial frame of reference. And so far we said center of the Earth could be inertial frame of reference. But it's not, because Earth is going around the Sun in a circular motion. If the motion is circular, there has to be acceleration, which means it's non-inertial frame of reference. But our solar system, entire solar system, is traveling around the center of the Milky Way galaxy, namely Sagittarius A star black hole, supermassive black hole, which means there is a Coriolis force due to that circular motion, which ultimately means we cannot find any perfect inertial frame of reference. Everything is rotating, accelerating, and so on. So, to the best of our knowledge, there is no perfect inertial frame of reference. However, the imperfections due to these external factors, such as the Earth rotating around the Sun or the solar system rotating around the center of the Milky Way, are so small that nobody really accounts for them, especially in the field of atmospheric sciences, wind engineering, and so on. Nevertheless, they exist, and it is interesting to think about these things. It is interesting to think, when I sit here, the amount of different forces and accelerations that I am exhibiting is just enormous, despite the fact I don't feel most of them, but they exist at some fundamental, very weak level, let's say. They exist nevertheless. In the next video we will talk about Rossby number. Until then, Happy New Year and see you in the next video. Goodbye.